Thanks. And then Matthew, you can start sharing. Okay, yep. So now we have Matthew Graydon, the University of Waterloo, and he's going to be telling us about his work on Euclidean Jordan algebras. So over to you, Matthew.
Right, thanks, Vicky. So I really would like to thank the organizers. I don't think this could have gone any smoother unless it was in person. So John and Anna, thanks a lot. And I would also like to thank the chairs. I mean, this has just gone so smoothly. So thanks a lot. I would like to tell you about some joint work with Howard Barnum and Alexander Wills. The moral of the story is that we've got a super theory, if you will, that contains quantum mechanics, but more. So this is a theory that contains state spaces that are isomorphic to, the ambient spaces are isomorphic to certain Euclidean Jordan algebras. And I'll explain what that means. So my plan for the talk, the first third, I'd actually like to just make some historical remarks and explain a little bit about where this mathematics came from. And in the second part of the talk, I'd like to lay out some axioms for composites of Jordan systems, and then present some classification theorems from our paper. And in the third part of the talk, I'm going to construct some categories. And the end result is that, so we've got a dagger compact category that contains all three, real, complex, and quaternionic quantum theories. So that's kind of the moral of the story. Right, just so we're all on the same page, a Jordan algebra. Can you see my mouse? Yeah. Okay, so a Jordan algebra is a unital commutative algebra over the real numbers where the Jordan identity holds. By an algebra, I mean a vector space equipped with a distributive multiplication, just for the record. So Max Born had a doctoral student in the early 1930s. By the name of Pascal Jordan. So actually the name is Spanish, it's Jorda. They emigrated from Spain and changed the family name to Jordan. But of course I can't help saying Jordan. So I will say that these are Jordan algebras. So Jordan had a really cool idea. If you start with an associative algebra, you can make new algebras from it. So this product here, A cross B, he considers it being some real number lambda times the associative product AB plus some other real number mu times the reverse BA. And Jordan points out that the case lambda equals minus mu corresponds to something that hadn't been named yet. So Weil had yet to name these Lie groups. So he called them continuous groups or something like this. The case lambda equals mu results in a commutative algebra, and Jordan emphasized that that was physical. And if you want it to be unital, that forces lambda and mu to be 1/2. Okay, so this is the canonical example of a Jordan algebra. You take an associative algebra and you impose upon it the anti-commutator scale by 1/2, and that gives you a Jordan algebra. The identity, the Jordan identity, may seem a little obscure. So in the next year, in 1933, well, first of all, Jordan was so bold to say that these are, on a possible generalization of quantum theory, right? So that's very interesting. The idea is not new. Originally, Jordan was considering this axiom. So he wanted the algebra to be power associative. And I should note here that juxtaposition does not denote associative multiplication. It's a Jordan product. So the axiom in its modern form came later. It came a year later. Let me say this. A Jordan algebra is formally real if it's finite dimensional. And if you take any collection of elements in the Jordan algebra and sum up their squares, if that's 0, then all of them have to be identically 0. Okay, so that's what's known as a formally real Jordan algebra. And once Jordan got together with von Neumann and Wigner, they were able to prove that the Jordan identity is equivalent to power associativity within a formally real Jordan algebra. And that's where we get the modern form of the Jordan axiom. This theorem is a big theorem in the field. They classified these things. So let A be a formally real Jordan algebra. The first part of the theorem is that you can decompose this in terms of a direct sum of simple algebras. And by simple, I mean the ideals are either the empty set or the whole algebra itself. Furthermore, every such simple formally real Jordan algebra is isomorphic to one of the following. So a Jordan matrix algebra, by that I mean precisely the set of n by n self-adjoint matrices over the real field, the complex field, or the quaternionic ring, equipped with the anti-commutator. So that's a Jordan matrix algebra. A spin factor. Here the Jordan product is a little different, but it's more intuitive to understand spin factors as follows. Their positive cones are future light cones in d+1 dimensional spacetime. And it's actually a curiosity that the qubit, so the qubit's a spin factor in 3+1 dimensions. And it's interesting that the quantum bit is a spin factor like that. And Marcus Mueller has actually shown that if you allow, so if you start off, you don't assume that you've got quantum bits, you've just got spin factors. I believe the main result is that if you allow it to carry certain representations of SO13, then it forces it to be a qubit. So the three-dimensionality of space kind of imposes that we have qubits. That was a really cool result. One more item on the list, the exceptional Jordan algebra. So these are the 3x3 actonionic self-adjoint matrices. Items 1 and 2 are called special because there's always a faithful Jordan homomorphism into the self-adjoint part of a C-star algebra. It was Albert, I believe it was 1931, who proved that M30SA is exceptional. So there is no faithful representation of these guys inside the self-adjoint part of a C-star algebra. So that's why it's called exceptional. Now, the title of my talk is not about formally real Jordan algebras. It's about Euclidean Jordan algebras. But okay, now we have this. I'm going to show you a simple proof that the same thing. A Euclidean Jordan algebra, I'm just going to define it. So it's finite dimensional. It's a Jordan algebra, equipped with an inner product enjoying this associativity axiom. So if you consider the inner product of A j prod B with C, then that's the same as the inner product of A b j prod C. So here's a fact. I haven't seen it in literature, probably because it's too trivial. The proof is really easy. So let A be a Euclidean Jordan algebra, and suppose that we've got a sum of squares equal to 0. We have to prove that they're each 0. Okay, so by linearity of the inner product, you can show that the inner product between that sum and the unit has to be 0. Now I apply linearity of the inner product again. Now I apply the Euclidean Jordan algebraic axiom. So you notice that A squared is A dot A, and then you move it over to the other side via the axiom. So now you've got this. Well, of course, then they're all 0. So a Euclidean Jordan algebra is formally real Jordan algebra. The converse is easily obtained by the Jordan von Neumann-Wigner classification theorem. Basically, what you do is you equip the Jordan matrix algebras or the exceptional Jordan algebra with the usual tracial inner product. So in quantum theory, this is the trace of AB, right? And for spin factors, there's the obvious inner product on d+1 dimensions, the dot product on those vectors, that serves as a Jordan product. So I'm going to say EJA a lot. This means Euclidean Jordan algebra. You might wonder why the set of observables or effects of a physical theory should carry any meaningful bilinear product at all. I mean, this is not obvious that it should carry. So happily, there is an alternative characterization of these things. I would like to actually now thank the previous speakers for sparing me the introduction to generalized probabilistic theories and convex cones. So I shall jump straight away to the following definition. A pointed convex cone in a finite dimensional real vector space is self-dual when the internal dual cone coincides with the cone. So you can think about the dual cone internally by the Riesz representation theorem. And we say that A plus is self-dual when that coincides, when that coincides with it, okay? Another definition. I will say that A plus is homogeneous when its automorphism group acts transitively on its topological interior. And here I'm referring to the unique linear topology. Quantum theory is like that. If you think about an element X inside the cone of positive semi-definite matrices, that means it's invertible And you can map that to any other element of, so say you've got another invertible element y in the count. So if you allow the adjoint, so the automorphism group acts via the usual adjoint action of the special linear group. So if you apply, for instance, y to the 1/2 x to the 1/2 inverse as the adjoint, then you've got x in the middle, and then x inverse to the 1/2, x inverse to the 1/2. Let's get rid of the x, and then you've got y to the 1/2, y to the 1. That gives you the y. So the cone is homogeneous like that. These have been classified independently by Cocker and Winberg. So A plus is homogeneous and self-dual if and only if A is Euclidean Jordan algebra. So these are the only ones. These are the only homogeneous self-dual cones. Homogeneity and self-duality have been derived from physical postulates. So I'm thinking in particular of derivations of quantum theory due to Barnum and Hilgert recently. So they were able to get Jordan state spaces from just 2 axioms. Also the axiomatizations of Alex Wills or Lucien Hardy, or I don't want to forget anyone, Carabella and company, and Marcus Mueller and Luis Massanas, and the rest are actually contained in a really nice book published in 2016 by Julio and Rob Speckens. So homogeneity and self-duality are getting narrowed down by physical postulates. So these are a very natural class of theories to consider. But there's a problem. So for a very long time, it was believed that it was not possible to take tensor products of quaternionic systems for the following reasons. One, tensor products of quaternionic modules don't exist. So there are no linear tensor products of quaternionic modules. Even worse, so there have been so many theorems, and I hope the authors will appreciate this. It's a theorem, but I'm going to call it a coffin nail. So the scalar monoid in any symmetric monoidal category is commutative. So if you want to consider generalizations of quantum theory and vary the underlying field, hey, I can't get the quaternions because they're not commutative. There is a workaround. It's a workaround that goes back to the work of Dyson. I learned this from a paper from John Baez, who actually goes so far as to integrate these things at the level of vector spaces, but he's equipping them with certain involutions that single out the real complex or quaternionic varieties. And we conjecture that by applying the CPM construction to Baez's implicit category, that you'll get a category of the type that we consider. So that's actually an open problem. Right, composites. Some axioms. So I'm going to say that a composite of Euclidean Jordan algebras A and B is another Euclidean Jordan algebra, plus a bilinear map from their vector space tensor product. That's what I mean by this R. I mean their vector space tensor product as real vector spaces. So plus a bilinear map such that if you take any 2 effects, so it contains product effects. The composite has to contain product effects. And no signaling. So if you've got a pair of, by omega I mean the state spaces. If you've got a pair of local states, then they should evaluate independently in product effects. So we impose that axiom, this non-signaling axiom. This one is just for normalization. So you want the tensor product of the units to be the unit. This one might not seem so obvious. So we demand that the image of the vector space tensor product generates the composite as a Jordan algebra. That condition can be lifted if you remove these axioms and take the fourth out, you'll get composites containing a composite generated by ABs. But of course, physics is more than just kinematics. We have to have some dynamical axioms. So I'm going to say that a dynamical composite is a composite together with a homomorphism from the Cartesian product of the automorphism groups into the automorphism group of the composite, such that local states can evolve independently under free evolutions. That's what this axiom number 5. So if I take 2 local automorphisms and apply them on a product state, so that should just be the local evolutions of the product state. So you have independent free local evolutions. This one also looks suspicious. It's possible that this condition is not required, but we haven't been able to prove it. But it's natural. It's natural in the sense that we'd like to construct dagger compact categories of these things. Basically, what I'm going to show you is that most of these composites are ideals in the following structure. So let A be a special Euclidean Jordan algebra. Then up to isomorphisms, there exists a unique universal C-star algebra and an embedding thereon too, such that the image of the Jordan algebra is a subset of the self-adjoint fixed points of an involution on its universal C-star algebra. Okay. Moreover, one has to have the image of A under its canonical injection generates the C-star algebra. I said it's a subset of the self-adjoint fixed points. And this is the cool thing. So the universal C-star algebra has this property that if you've got a Jordan homomorphism from A into the self-adjoint part of any C-star algebra, then that factors through the universal C-star algebra like this. Hansche-Olsen defined what he called the universal tensor product. I should say that he did this in the infinite dimensional case, by the way. I'm restricting attention to finite dimensions for now. The universal tensor product of two special Euclidean Jordan algebras is the Jordan algebraic closure of the real vector space tensor product of their images upon injection into the universal C-star algebra. So you inject these things up, and then you close under the Jordan product. And that's what Hansche-Olsen referred to as the universal tensor product. I'm going to skip these details and just go to the classifications. Theorem 1. So if AB is a dynamical composite of simple, non-trivial Euclidean Jordan algebras, by non-trivial, I've already defined simple. By non-trivial, I mean that they are not isomorphic to a direct sum of one-dimensional trivial Jordan algebras. So if I have a composite of such things, then it's isomorphic to a direct sum of Jordan matrix algebras, each with rank bigger than or equal to 4. That's just to tell you that you're not going to get the quaternionic bit as one of the factors. So the main message is that the composites are special, okay? Theorem 2. If I have a dynamical composite of arbitrary special Euclidean Jordan algebras, then it's isomorphic to a Jordan ideal in the Hansche-Olsen universal tensor product. Okay, so all these composites have to be ideals or the full thing in the tensor product that Hansche-Olsen defined in 1983. The octonions, they can't play with everyone. So if I have two Euclidean Jordan algebras, no restrictions. And if A contains an exceptional ideal, meaning that there's a direct summand of A isomorphic to the 3x3 self-adjoint octonionic matrices, then dynamical composites with B do not exist, except when B is trivial or classical. You can take this as meaning that octonionic systems can compose with classical systems, but not quantum systems, or not real quantum systems, or not quaternionic quantum systems. Okay, this is okay. Now I'd like to tell you how to make some categories out of these things. I'm going to need to make another definition. An EJC algebra is a triple with A Euclidean Jordan algebra and A finite dimensional C-star algebra, and pi A unital Jordan monomorphism from A into the self-adjoint part of A. And by a monomorphism, I mean an injective homomorphism. The canonical tensor product of EJC algebras is going to be defined, the algebra part is going to be defined as the Jordan algebraic closure of the real vector space tensor product of the images of these algebras inside their C-star algebras, okay? So that should sound familiar from the previous slide. So by definition, AO.B is contained within the self-adjoint part of the C-star algebraic tensor product of their C-star algebras A and B. Now here's something maybe, oh right, morphisms, right, morphisms. So let K be a class of of EJC algebras. Let A be two members of this class. A CJP map relative to K from A to B, it's first of all a positive linear map between their C-star algebras, such that for any other object in that class, if you compose phi with the identity on C, then that's positive. But it also has to take the canonical inner product of A with B to the canonical inner product of B with C. And here's a theorem. So let K be a class of EJC algebras. It has to, so we assume that it contains the unit, and we assume that it's closed under composition. Okay, so you've got a class that's closed under composing, and it has the unit in it. Define a CJPK to be the category whose objects are from K, and the morphisms are CJP maps relevant to K. Then that's a symmetric monoidal category, albeit in most cases one that is very far from compact closed. So here are some examples. The category RSE it's basically it's obtained via the CJP construction of the Jordan matrix algebras in their standard representations. Okay, so here's how the tensor products work up here. Real with real is real. Quaternionic with quaternionic is real. And the complex systems almost act as an ideal, right? So you'll notice that if anything interacts with the complex system, it becomes complex. Right? So I hesitate to say this. A wild speculation would be that if the universe began with all three types, then as they interacted with complex systems, quantum theory began to dominate. But that's just a wild speculation. So quantum theory is a subcategory. Real and quaternionic quantum theories form a subcategory. So this goes back to Dyson. You have to take them together. There doesn't seem to be a sensible way of isolating quaternionic quantum theory and forming reasonable composites therein. So they sort of have to peacefully coexist together. So as I said, this is not dagger compact. We can do a little bit better. So Uru has objects, Jordan matrix algebras, save for the quaternionic bit in their universal embeddings. So they're embedded into the universal C-star algebras, and the morphisms are CJP maps. Okay, so basically what's different here is that complex systems get embedded sort of into a double. If you've got a complex quantum effect, it's embedding the first sum end is A, and the second sum end is A transpose. An interesting, basically how our proofs work is that we showed that a CJP map in this category has to be a CP intertwiner. So it has to intertwine the canonical star anti-automorphisms in order to be completely Jordan preserving. And that really simplifies some of the proofs. Right, and there's a really cool feature of this category. It's as we would like. So states and effects are both isomorphic. There's an affine isomorphism between the states and effects and the positive cone of these Euclidean Jordan algebras. So this is much more well behaved. But I'm going to do a little better because you'll notice that the quaternionic bit still isn't in there. Okay. I will say I'll need to make one more definition. I'll say that an involutive EJC algebra is an EJC algebra for which there exists a unitary order 2 star anti-automorphism. And by anti-automorphism, I mean a linear automorphism, but it switches. So 5AB is 5B times 5A. So that's the anti part. It doesn't mean anti-linear. Okay. So these guys are the self-adjoint fixed points of the involutions. They're not a subset. They are exactly the self-adjoint fixed points of their involutions. It is a theorem that their canonical tensor product works like this. And that really simplifies the calculation of what these tensor products are. If K consists strictly of involutive AGCs, then all of the CJP maps are once again CP intertwiners. And this is how the tensor products work. It's very similar to what I showed you before. However, notice that complex quantum systems come equipped with an extra 0-1 valued superselection rule. Basically what this does is it functions to make the transpose a valid morphism. So if you perform the swap then that affects the transpose. Another wild sort of speculation. So you essentially have two sum ends, 1A and 1A transpose. Now the transpose is sometimes regarded or associated with models of time reversal. So one could regard these composites as quantum theory, where in the first sum end time is running this way, and in the second sum end it's running backwards. Okay, but this is another unproven wild speculation. The category InVQM, this is going to be the final one. The category in INVQM, so the INV is for involutions, but it could also be read INV quantum mechanics, because our composites, except for quantum ones, they're not locally tomographic. Okay, first of all, these are not locally tomographic, and sometimes preservation of purity is violated. So for quaternionic composites, it's no longer true that the composite of two pure states is a pure state. Okay. So these composites have some properties that might cause them to envy usual quantum theory. In any case, and the morphisms are CP intertwiners. Okay, and the theorem is that this is a dagger compact closed symmetric monoidal category. I'm conscious of the time, so I'd just like to close with some open questions.